Recording is rolling. Let's watch some Paul Hewitt demos on the first law of motion.
I got a couple of blobs. These are blobs of clay. These clays have inertia. Right now they're at rest. They tend to stay at rest. I can put this clay on the top of my head like this, and I can see this one very clearly. But you know, how can I see that one without touching? So I turn around. Things tend to stay put. You ever do that? You got a bowl of soup, right? And you got the alphabet, and you want this alphabet over here near you, so you turn the soup bowl, and what happens? The alphabet stays there. You keep turning the soup bowl. Inertia. Things at rest tend to stay at rest. And what do we have down here, gang? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that? Here's a ball. Hold it up here. And the ball is hanging. Now what I'm going to do is I'm going to pull this string. Bam, 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 harder, 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 until either this string or the string's going to break. Which one do you think will break? I'm pulling that down. Don't I exert tension in the string? Doesn't the string get tight? Huh? Fine, huh? Doesn't this one get tight too? And so I have a tension here. I also have a tension here. The string is stretched out. So as I pull gradually, which one's going to break again? Top or bottom? I'm going to say the top because I got another string here for the next trial. Let's watch this. Was the top? Because of the weight of the ball or because of the inertia of the ball? Check your neighbor and see if your neighbor sees which of the two properties, weight or inertia, made the top string break. Go. Why did the top string break? Because the weight of the ball is acting up here too. So the weight of the ball pulls on the top. The weight doesn't act on the bottom string. So I've got the weight of the ball pulling on the top string and the tension with which I pull on the top string. Both these, boom, it breaks. But how about now I take the string and I whip it down quickly like that. Why did the bottom string break? Because of the inertia of the ball or because of the weight of the ball? Check your neighbor. I can show you that with this elastic gang. This elastic. If I pull, I can pull. Look how much that thing's stretching. Okay, but let's suppose I just go like this. Notice that there was not as much force up here. The elastic didn't stretch as much when I pull quickly. That force was not transmitted up here. The inertia of that ball, it wants to sit right there, honey. And I pull, it stays right there. Another word for inertia is lazy. Okay? The ball is lazy. It tends to stay doing what it's doing. Is that neat? This has got a lot of mass, gang. To say it's got a lot of mass, to say it's got a lot of tendency to stay right where it is. Okay, I'm going to lay on here. Would you put the anvil right in my stomach, please? Right in my chest. Okay, right here. Okay. Now, would you get on the other side and slam that thing as hard as you can? Over here, Troy. Oh, please don't miss the anvil. Do you have any grudges against your teachers? Hit it harder. We talk about forces. We're going to talk about forces not in terms of pounds, gang, but in terms of newtons. Here's a Newton scale. Here's a kilogram. I'm going to weigh the kilogram. And the kilogram has a weight. gravitational pull of almost 10 newtons. Want to get strict? 9.8, but we can say 10 newtons. So 1 kilogram weighs 10 newtons, 10 newtons of gravity force. You show me a system that's accelerating. And by that, I mean a system that's changing its speed, okay? Some system that's doing this. It's got a change in velocity over some particular time t. Anything that's changing. You show me a system that's changing how it's moving, and I'll show you a system that must have an unbalanced net force. In chapter 2, we said this is what acceleration is. Acceleration is a change in velocity with respect to time. That's what it is. Acceleration is change. It's change how you move. Now we're saying how you get it, how you produce it. And we're saying now you produce an acceleration by pushing on something, by applying some net force. But how much acceleration depends upon the amount of matter. This idea is Newton's second law of motion. But let's suppose you asked a little kid who's very, very bright, but ignorant, never seen it before. You say, kid, I'm going to drop these 2 objects. You tell me which one hits the ground first. I'll give you a Hershey bar. Kid says, with almonds? Yeah, with almonds too. All right. You tell me which one hit the ground first. And the kid says, well, can I feel those things first? You say, yeah. The kid take this. He says, it's a pretty heavy piece of metal there. It's aluminum, but there's enough of it. So it's kind of heavy. Big gravity force acting on that. Kid take this. Oh, this little tinky ball. See, it's not very heavy at all. It's very, very light. God, doesn't weigh anything. Come on, kid, which one hits the ground first? He said, well, obviously, the heavy metal going to hit the ground before this little red ball. You say, how come? I think, well, it's more force acting on it. I know when I'm pulling my toys, if I pull with a big force, it got a big change in motion. If I pull with a little force, only change a little bit. There's more force, more gravity force acting on this. Boom, gonna hit the ground. Give me my Hershey bar. Then you take it and drop these things. The kid's like, they fell together. Kid didn't get the Hershey bar. You know what that kid is saying? That kid is saying this, that the acceleration, change in motion, is directly proportional to the force. I got a question for you. Is that kid correct or incorrect? Begin with a C. It's correct. His thinking is fine. But you know what? The experiment doesn't line up with his thinking. One of the beauties of science, we can experiment to see if our thinking is complete. Let's suppose you ask some other kid. I know they live in a different part of the island. You ask the kid the same question. Hey, kid, which one going to hit the ground first? The little dinky ball or the heavy weight, huh?
All right, I'll save the rest of that one for later. Hey guys, have a great rest of your day.